Welcome to exercise 6, photovoltaic energy systems. We will discuss today wiring losses, inverter losses and so on. And you see here our first task we have to do. How big are the wiring losses absolutely and relatively for a Cooper cable on the DC side, considering maximum power point operation, and that each of the 40 modules, what you see below, have the following data. So we have the voltage in the maximum power point is 36.1 volts and the current is 8.3 amps, also in the maximum power point. The specific conductibility of the Cooper cable is 56 meters per ohm per square millimeter. The resistance of the wire is defined as R divided by big L divided by A. So that's the cross-section area of the wire divided also by the kappa, not K, the kappa, the specific conductibility. While big L is the length of the wire. So take a look at the conduction diagram. So we have 10 modules interconnected in series, and these go to the DC connection box, and so do the other 4 strings, each with 10 modules, so 40 modules altogether. While the modules installed have some extensions, the cable length are different. So we have, for the furthest away string, we have 18 meters. For the next we have 16 meters, then we have 40 meters, then we have 12 meters for each pole. So as well as for positive as for negative. So let's calculate it. First we calculate the losses. So we calculate the loss for each string separately because they have different lengths. And together we add those up. So we have here the currents which go through it times the different resistances. And we have here the resistance of the main cable here. Go back a little bit. So here you see it's still the main cable. So this is after the connection box to the DC switch. Sometimes it is also integrated in the box, as you saw. It's a picture in the image, but here it's separately, and we have to bridge a length of, how many meters is it here? 8 meters. And we have a different diameter of those. So this is 16 millimeters in square, also of a Cooper cable. Then comes the DC switch, and this is very close to the inverter. And then you have AC, which goes into the public grid. But we have to calculate the DC side only. So only all the cable lengths up to the DC main switch. So this is a formula for those. So the first is the sum of the losses at the different strings plus the losses at the DC mains. So the cable resistance of each string we have for R1, the furthest away, is 2 times, because there are 2 poles, 2 times 18 meters divided by 4 square millimeters times 50. This is a kappa here, 56 meters divided by ohms divided by square millimeters. So the resistance is 0.161 ohm. For the next a bit less, because the distance is a bit less. So we have 16 meters only, and the resulting resistance is 0.143 ohms. The next is only 14 meters away, and the according resistance is 0.125 ohms. The last is at 12 meters distance only, and it has a resistance of 0.107 ohms. The DC mains, this has a much higher current, but the diameter is also much larger. It's 4 times, so it's 16 square millimeters, and so the diameter is not 4 times, but the cross-section area is 4 times. So we have 16 millimeters in square. The distance is 8 meters, and the according resistance is 0.018 ohms. So the voltage at each string of the modules is, so we have the sum of the modules, because we have the modules interconnected in series. So we have each module has the voltage in the maximum power point, and we have to add those up. So it's 10 times that voltage. The current stays the same, so we can take the simple current then. And the current at the DC main is 4 times that current, because all strings are interconnected before the DC mains. So if we put in, this is the same formula as above, just we put in the values, and we have here the losses of 56.76 watts. The relative losses, so we have the losses with 56 watts, and the total power output is then, so we have 40 modules. Each of them has a voltage in the maximum power point and the current in the maximum power point. We calculate that here. So the total power is 10 times, so see here, 10 times the voltage of each module in the maximum power point times the current in the maximum power point, because you operate those modules in the maximum power point, not in open circuit conditions or short circuit conditions. And then the total power output is 11,985 watts. So in relative terms, so we have 56.76 watts divided by 11.985 kilowatts. So the relative losses are 0.474%. Next task or next question is, how much are the accumulated losses of PV power of the exercise 6a, so the task before, worth if you consider a lifetime of 20 years, the value of the energy losses of 0.1 euro per kilowatt hour. So that's a typical value. What you, if you have in Germany a house and put some PV modules on it, then you can generate electricity for about 10 cents per kilowatt hour or 0.1 euro per kilowatt hour. And the specific annual energy generation yield of 900 kilowatt hours per year per kilowatt peak installed. So this kilowatt peak means that it's the power in the maximum power point under standard test conditions. This is a quite typical value in Germany. Sometimes if you go to southern Germany, you can reach 1000 kilowatt hours per year per kilowatt peak installed. But for Paderborn, 900 is really realistic. Does it make economically sense to increase the Cooper diameter of the cables? So we put in the thicker cables, the losses are reduced, but while we use more Cooper, the costs are increased. The cost of original 4 square millimeters at 55 cents per meter. If we increase them to a cross-section area of 6 square millimeters, the costs are 0.72 euro per meter. And if we go from the DC mains from 16 millimeters in square, which costs 1.81 euro per meter, and we increase them to 25 square millimeters, the costs are 3.19 euro per meter. Let's do the calculation, the same as before. So we first calculate the losses over 20 years. So we know the specific losses at the moment, and we accumulate it over a year or over 20 years. So we have the generation during 1 year of such a power plant, which is 900 kilowatt hours per kilowatt installed. And we have 11 kilowatt, a bit more than 11 kilowatt, and we calculate the relative losses and calculate it over 20 years. So the electricity generation during 1 year, this is here with a specific yield of 900 kilowatt hour per year per kilowatt peak installed, times the power under standard test conditions in the maximum power point of our power plant. And we have 10,787 kilowatt hours or 10.787 megawatt hours per year. This is our electricity generation from our power plant. Next step is to calculate the losses. So we know we have the relative loss factor here, which is 0.00474 or 0.474%. And if you put in the numbers, you come to about 1 megawatt hour or 1021.73 kilowatt hour for 20 years. So over 20 years, we lost about 1 megawatt hour. So this 1 megawatt hour is worth 0.1 euro per kilowatt hour. We have then losses, monetary losses in about 102.17 euro. So the second part is if the extra costs of the thicker cables are lower than the value of the avoided losses. So the value of the avoided losses is 102.17. This makes economically sense. So if the cables cost more, for example, 200 euro, it doesn't make sense. If they only cost 50 euros, it makes perfectly sense. So what we do, we recalculate the value of the losses with the thicker cables, get the difference to the original losses and compare it also with the additional cable costs. Let's do the calculation again. So here we have the losses in total. We have now the modified resistances. So instead of 4 square millimeters, now we have here written in bold as 6 millimeters. And the furthest string away has a resistance of 0.107 ohms. The second string, it's closer, only 16 meters away, and its resistance is with the 6 millimeter square cables 0.095 ohms. For the third, it's 0.083 ohms, and for the closest, it's 0.071 ohms. The new mains with the increased diameter, we have then the resistance of 0.014 ohms only. So the voltage is still the same. So over the 10 modules, the voltage and the maximum power point. The current stays the same through each strings, and we have 4 strings in total. This has to be considered in the mains. We put in the numbers here, and we arrive at loss here of 39.95 watts. So just take a look. It's reduced. Yes, it has to be. So this is always a proof if you are in the test or so. Just check whether the results are reasonable. So if you would have a higher value here, you calculated something wrong, or if it's extremely different, because we just increased the diameter by, how much is it, 50% or so. So for example, the losses can't be only a tenth of the original losses. So this result sounds perfectly reasonable. And also, if you do the calculations, take a look on the units you have here. So losses is in watt. So this is should also come out of your calculations. The power losses. If you have energy losses, must be watt hour, kilowatt hour, megawatt hour, and so on. The relative losses. So we divide that by the total power output of our power plant. It's the same as before. So it's still 11.985 kilowatt, and the relative losses are 0.33% only, compared to the 0.47% as before. So we calculate the amount of losses during 20 years. To go to the second line here, and these are 719.13 kilowatt hours. The values of these losses is 71.91 euro. So compare that to before, it was 102 euros. So we saved about in the vicinity of 30 euro. So we have to check whether the costs of the values are more than 30 euros. Then it wouldn't make economically sense. If they are cheaper, it would make sense. So we got the costs for the different cables, as before, printed here in small. So these were 0.55 euro per meter for the 4 square millimeter cables, and they increased to 0.72 euros per meter for the 6 square millimeters cables. And for the original cable, it was for the mains, DC mains, it was 1.81 euro per meter, and with the increased cross-section area, it is 3.19 euro per meter. So we put in numbers. So the total length here is 120 meters of the cable for the module wiring, and the length of the DC wiring is 2 times 8 meter, 16 meters. Then we calculate the cable costs. So this for the original cables, it was 68 euros for the module wiring, and for the DC main wiring it was 28.96 euros. Now we calculate with the thicker cables, then we have higher specific costs. The length stays the same. So we have for the wiring of the modules, we are at 86.4 euros, while we have for the DC mains cable a cost of 51.04 euro. So the value of the cost reduction, just to make the quiz estimations already before. So the value is originally we had a loss of 102.17 euros. With the new thicker cables, we have only a loss during 20 years of 71.91 euros. So we have a loss reduction of 30.26 euros. Let's see the values of the cable. The cable costs for the thin cables is 94.96 euros for all cables. So this is the module wiring cables plus the DC main cables. Altogether is 94.96 euros. For the thick cables, 147.44 euro. Here you already see that the difference is more than 30 euros. Exactly, these 52.48 euros. These are the additional costs for the thicker cables. And if we compare that to the reduced losses, we have a loss, a monetary loss of 22.22 euros. That means it doesn't make an economically sense in this case. So if you, for example, negotiate or you find a supplier of cheaper cables, it could make economically sense. But that's a typical calculation. So also the prices, what I gave you, are quite realistic to what's done, because nowadays the competition is really high at large-scale PV power plants, and you have to really do such calcs and negotiate also with the suppliers how to optimize in terms of energy yield, but also in or mainly in monetary terms. It's quite cumbersome. There are computer programs which do that, but also sometimes you have to do it manually. So for the exercise 6C, we compare the formula below, which was given in a guidebook. This is how to calculate the cross-section diameter. So this is L, the length, times the power. Then you have the power loss, or the desired power loss, divided by the actual power, times the voltage in square, times kappa, the relative resistance of your cable. So this is not given here, but you can do it at home and see whether this formula is correct. And the original calculation you have had before. So if you just do it manually and don't use the predefined formula as given here from the guidebook, maybe you see some differences. Then we come to the inverter calculations. So you remember this graph from the lecture. And we have here a curve of the efficiency at different load conditions. So this is full load. The conversion efficiency of that inverter is 95%. If you go to partial load, for example, here to 10% of the load, the efficiency is going down 96.8%. That's still quite good. Formerly, the inverter efficiency sank considerably for partial load. So nowadays, they are already in a quite high level. And in order to make the inverter comparable with a single number, people invented the so-called European efficiencies. That means you don't pay so much account for the full load conditions, but here the main focus is on the 50% load here, which has a weight of 48%, while the full load conditions only account for 20% of the result. And also you take into consideration several partial load conditions. For example, here at 30% of the load with a weight of 10%, at 20% of the load with a weight of 13 or 0.13, or at 10% of the load, as we saw before, with a weight of 6%, and for 5% of the load with a factor of 0.03 or 3%. So we put just in the numbers here what you find here and put the different weights here. So we start with the full load conditions here with a weight of 0.2, 95% of conversion efficiency, or 0.95. Then we go to the next at half of the power output only, which is considerable more, with a weight of almost 50%, so 0.48. And the efficiency is almost the same. It's even increasing a bit. Here the inverter manufacturers are improving that, so they just have in mind those European efficiency in order to get good results there. Formerly, the maximum of efficiency was always at the full load condition, and then it sank steadily. And here we have just the maximum efficiency here at half of the load. And so on. You continue that here for 30% of the load here, that, and so on. You just take into consideration. You just to add it up, and then you come to a value of 0.94 for the European efficiency. How many PV modules can be connected in series conditions? Each module has a power of 300 watts with an index P. That means under standard test conditions. And considering the data sheet, which will be given on the next slide, in the German conditions, which parameters have to be considered if you do such a calculation? So the site conditions are the maximum permitted system voltage are typically 1000 volts, and the maximum input voltage of the inverter is 1100 volts. So we have to decide which is a more stringent conditions. These are the maximum system voltage with 1000 volts. The conditions by the inverter is less strict, which is 1100 volts. So we apply the lowest 1000 volts. It could be also vice versa. Sometimes you have inverter which only can digest 900 volts and so on. But in this case, the most strict conditions or most strict site conditions is the maximum permitted system voltage, which should not be exceeded. The open circuit voltage is now relevant, not the voltage under maximum power point, because if you have under some circumstances no load there and the voltage goes up, it may destroy the inverter, or you exceed the maximum system voltage, which could also lead to a damage or cause an alarm and so on. So this has to be considered, and under standard test conditions, this voltage is 39.82 volts. If you consider the given data sheet conditions, this is under standard test conditions. Remember, standard test conditions are at 25 degrees of model temperature, but it's written for German conditions. So you have to also consider winter. So the operation conditions can be lower than the standard test conditions. And for example, if you in the morning, usually the time before sunrise is the coldest, and then temperatures of minus 20 degrees Celsius may occur. And when the sun goes up, it takes some time until the module warms up. So you have to calculate with a module operation temperature of minus 20 degrees. And remember, if you go back to the lecture where we have the curves at different temperature, the effect on temperature on the IV characteristics. So you see here that at increased temperature, the main effect you see on the x-axis is the reduction in voltage. It's about in the vicinity of a crystalline solar cell, minus 0.4 to minus 0.5% per Kelvin temperature increase. So if you increase the temperature by 10 degrees, you have about a 5% voltage loss and also corresponding power loss. The increase in current plays a very minor role. So you see here, we have a standard test conditions, STC called. This is all measured at an operating temperature of the solar cell of 25 degrees. You see if you lowering the temperature, the voltage goes up. So we have to consider the increase in voltage, which also occurs as well as in the voltage in the maximum power point, as well as the open circuit voltage. So we take from the data sheet the relative temperature coefficient, which is in this case minus 0.31% per Kelvin for the voltage. So we take a look, how much is it the voltage increase? We take a look at the difference to standard test conditions. So we have here minus 20 degrees, minus 25 degrees. So the temperature difference is 45 Kelvin. Learned this in, sometimes you see also in literature that temperature difference is 45 degrees Celsius. But usually I learned that temperature differences are usually given in Kelvin. This is negative. That means if you have a negative temperature difference multiplied with a negative temperature coefficient, you arrive at a positive factor for the voltage increase. So if we put in the numbers here, so this is the formula here. You have the formula for the relative increase in voltage. So delta open circuit voltage divided by the open circuit voltage is the temperature coefficient times the temperature difference. You put in the numbers here and you have a relative increase of 13.95% or 0.1395. If you put in the numbers here, 0.1395 times the open circuit voltage under standard test conditions, you come to an increase of 5.55 volts. So this is for one module only. To calculate all for the other modules, the one module then has an open circuit voltage which should be considered in the calculations of 45.47 volts, not anymore of the original numbers. So many students in the test, they don't consider that issue. So we calculate the maximum modules in series. So in series conditions, the voltage add up. And the conditions are that the maximum voltage is 1000 volts. And usually you have the number of the modules times the open circuit voltage under operating condition of each modules, and this should be lower. So we already put this in the lower part here. So we have 1000 divided by the open circuit voltage at minus 20 degrees Celsius, and we come to a number of modules of 21.99 modules. So this is a bit unfortunate. So you almost have 22 modules, but if you're really strict, you only would be allowed to connect 21 modules. Sometimes if you take a look at the real local conditions, sometimes there are locations in Germany which don't have such cold temperature. For example, if you go to the coast, then you say, okay, there is only minus 19 degrees or minus 18 degrees, then you could arrive at 22 modules. But if you're really strict, you're only allowed to interconnect 21 modules. How many modules can be interconnected in parallel? So from the module side, there's no restrictions because we have the only limitation was the maximum system voltage we got here. But for the inverter side, we have to take a look at the data sheet of the inverter. the maximum inverter short circuit current is 30 amps. And the maximum inverter MPP is 22 amps. So we have two conditions then, and which is the stricter one? This is the maximum inverter MPP. Oh no, we don't know yet. Sure, at the modules also the short circuit current might be a bit higher. Then we have also to calculate the worst conditions. So we have a positive temperature coefficient. It's low, but it's positive. So we have to consider the maximum operation temperature because this increases the current. We have from the data sheet now here we have the temperature coefficient for the current, which is plus 0.043%. It's much less, this coefficient, but it's a positive. And this is the percent per Kelvin, so the relative increase in current. We consider the temperature difference, so we have 80 degrees considered maximum operation temperature, minus 25 degrees. Then we have an increase of 55 Kelvin compared to standard test conditions. And if you put in here the temperature coefficient, we have here an increase of 2.365% for these conditions. So we go up here, you see here in absolute terms. So this is the current and the standard test conditions of one module, and then we have the relative increase of 0.02365. Then we have an additional current of 0.223 amps. So it's not really a lot, but let's see whether it makes some difference. So there were the two conditions because there was either the limitations by the short circuit current or by the current at the maximum power point. We choose the current in the maximum power point because this is more critical to the inverter restriction than the IEC. The temperature coefficient should be the same. And then we have here the current under these conditions is 9.63 amps. And we have here the maximum permitted current in the maximum power point is 22 amps divided by this 9.36 amps. So we have a factor of 2.28. So we can connect two modules in parallel only, or two strings in parallel. So the last question is how the system design has to be changed when we use tracking systems. Yes, considering shadowing of each other, there has to be considered the maximum current, and the changes also in operation temperature may cause a difference. These are the data sheets. So this was a string inverter by Huawei, and here you see the values. So it's a typical engineering task. So you get the values from the different suppliers, and then you have to make an optimized system layout technically and also economically. Consider the limitations by the different components you put in the system. So next part of the exercise, we have here a load consists of 5 LED bulbs of 8 watt each that are operated for 7 hours a day through the whole year. An irradiance measurement of the desired location. They should be in the southern hemisphere at the Porto Alegre in Brazil. So we have switched seasons. That means in December we have the highest irradiance, while in June, July we have the lowest irradiance. You see here those values, accumulated values for a typical day of the month. So you have in January 5.97. The units are kilowatt hours per square meter per day. For February already the sun is a bit lower point, so it's 5.5 kilowatt hours per day only. And it goes on for equinox or around equinox in March. We have 4.97 kilowatt hour per square meter per day, and so on. and you have the lowest here in June with a value of 2.42 kilowatt hour per square meter per day. So you see, this is about a bit more than a factor of 2 between the typical day in the worst months to the best months. In Germany, it's much more severe. It can go up to a factor of 10. So what we have to do, you choose a 12-volt lead-acid battery. So this is still very often used. It's now gradually substituted by the lithium-ion batteries. But still, for many countries, a lead-acid battery is still the best option, or the cheapest option at the best. We should consider a depth of discharge of 50% only. Why? Because the lifetime of a lead-acid battery depends very much on the depth of discharge. If you fully discharge a lead-acid battery, it only doesn't even survive one single year, especially at the higher outdoor temperature. If you discharge by 50% only, it may last for 3 years or so. So this makes much more sense, or 4 years even. Depends on the type of battery you have, and you have to take this data from the data sheet or measure on your own. So, but always a good value or rule over the thumb is that you discharge lead-acid battery or stationary lead-acid battery by 50% only. You should give an autonomy of 2 nights, no seasonal storage, and the energy efficiency of the storage is about 80%, you should consider. So days of autonomy of 2 nights, because it's in the tropics, that's quite reasonable value only. So that means that you could survive a day without any sunshine, which is never the case, but as a rule over the thumb, it's okay. It could be also 4 nights or 4 days with a little sunshine. This depends very much on the local weather conditions, so you have local weather data. So first task is to calculate how much electrical energy has to be generated to supply the load and compensate the battery losses. So we have the actual energy to be generated by the PV generator, WPV. Then you have the sum of the loads divided by the efficiency of the charge controllers and the efficiency of the battery and the efficiency of the inverter. While you didn't have any inverter in, so we can consider the inverter efficiency by 1. Battery is given, so we have a conversion efficiency of 0.8, and the charge controller is not given, so probably it's included in the conversion efficiency of the battery. So we put in the numbers. So we have 5 light bulbs of 8 watt each. They are operated for 7 hours. So that's our daily consumption divided by the efficiency of the battery. We have to store the whole energy because usually you don't use lights during daytime, use it only during night times. And so the battery has to store the full amount of energy to be generated during daytime and supplied at nighttime. So you have to calculate to consider the efficiency of the battery for the whole system or for the whole time. Then you end up at energy to be generated of 350 watt hours or 0.35 kilowatt hours. So what is the necessary capacity of that 12 volt batteries? Can give it both in watt hours, but usually if you go to a shop, they have 12 volt battery and they have different ampere hours. So we just calculate also the ampere hour value. So the energy to be stored in the battery, if you would use 100%, it would only exactly this value, but you only want to discharge by 50%. So the size has to be double. Also, you have to consider that you want to have an autonomy of 2 nights. So you're not only calculating one cycle of 1 day and 1 night, you consider a reserve of 1 extra night because there could be bad weather conditions for 2, 3, 4 days. And this is included in this autonomy of 2 nights. Then you end up here at value of 1.120 kilowatt hours for your battery. In other words, if you calculate it in ampere hours, so you have this 1120 watt hours divided by 12 volts, you come to a value of 93.33 ampere hours. So just a short repetition, a layout of a small off-grid PV system. So this was our receipt, how we proceed here. So we first determined the load. We did already. So we have this light bulbs and the number of hours, number of light bulbs, and we consider the load. Then we determined already the battery size. It includes the days of autonomy, the depth of discharge, and so on. This we also calculated. Then we have to calculate the energy to be generated by PV. This we also calculated. And then we go to the daily irradiance at a typical day of the worst month of operation, because the system has to operate the full year and you don't have seasonal storage. Otherwise you would need very big batteries if you want to store the energy from December to June, which is the lowest irradiance of the worst day. So we just consider daily operation, and then we have here the worst typical day in the worst month of operation is June, and we put in the numbers and then we calculate the adequate size for that. Sure, we would have a surplus in summer, which we cannot use, but it's cheaper than to have a seasonal battery. So we have the area of the PV generator. So this is the energy to be generated by the PV generator divided by the conversion efficiency of PV divided by the daily irradiance per square meter, what we given for a typical day and the worst month of the year. Also, we can calculate the power at STC, but usually you don't buy it by square meter, you buy it by STC value, and that is given here. So you have the irradiance under standard test conditions times the area of your PV times the conversion efficiency, or if you put in the formula above here, you have just the irradiance under standard conditions, remember 1000 watt per square meter, times the energy to be generated, the daily energy to be generated by your PV generator, divided by your daily value of irradiance per square meter for the worst month of the year. So we do that, so we put in the numbers and then we come to this value. So you can use the first formula here, go by this one. But the problem here, we don't know the conversion efficiency. You can either calculate it or use the second formula here, which is free of the conversion efficiency. So we do this formula. So we have here power under standard test conditions is the irradiance under standard conditions, and the area and the conversion efficiency both don't know these values, but we can eliminate it by using the formula before, and we just have this formula as we discussed before. We put in the numbers. Irradiance under standard test conditions 1000 watt per square meter, energy to be generated 350 watt hours per day, and the irradiance for a typical day in the worst month of the year is 2.42 kilowatt hours per square meter per day. So the day gets eliminated, and also the same happens to the watt hours. So we have just the square meters, which gets eliminated here. So we have just left watts. And that's what we want. So this is a power under standard test conditions. So we have a power of 144.63 watts. So we size the same for Paderborn. There's longer winter periods, as you probably perceived now. Just we need more illumination. So it increased from 7 to 10 hours. So we have a higher need for energy to be generated, and also the worst month of the year, if you take a look at the tables, then the size considerably increased, also if you consider the increased days of autonomy. And it's not a day in June, but it's a day in December, because here we have 833 watt hours per square meter of the day only. The days of autonomy don't play such a big role for the size of the generator because it's leveled out, but for the battery it would play a role. But you see it's considerably bigger, so this is 4 to 5 times bigger than the necessary size for Porto Alegre. So here you have the irradiance value this is for Paderborn, the different months, and you have here different values. So the first column is the irradiance at the horizontal plane. Then you have the irradiance at the optimally tilted plane. So the adequate optimal tilt angles are here. So sure, you're in winter, you have a higher tilt angle, and then you have a fixed tilt angle, so at 30 degrees, so you have this value, which is more realistic. This is usually only valid if you have a tracking system or single axis tracking system, which you have an optimal tilt angle, but not the azimuth angle. You see here, okay, there is some differences, but not really very big. So the optimal over the year is a 36, and this column here is calculated for 30. You see here by the values it's not very big. So while we have now autonomous system, we differ from the design layout that you take the best value for having a maximum annual energy yield. You take the worst months that you want to have the best results for the most critical month. And this is December. And what you do is that you increase the angle here. Then you have a considerably higher output for these conditions. Sure, in summer it offers a disadvantage, but here it's quite advantageous. For this inclination angle, we don't have the results in summer and so on, but it will be lower. So for homework, also consider that the duration of light use has increased from 7 to 10 hours. How the system would change if you would use a 3-month storage. That means we discussed it a little bit before. So you have in summer, you have excessive power, and if you would store that power, how big this has to be and how much would it cost. So the prices are given below here. We want to calculate first the electricity costs. So you have here for the PV, including installation and stand and so on. This is a typical value, 1.5 euro per watt peak, lifetime of 20 years. The lead acid battery, 250 euro per kilowatt hour. Of gross capacity, you have to consider the usual capacity because you have to consider the depth of discharge of 50% only. Lifetime in Paderborn, because it's colder, it's 10 years. While if you have battery which is rated 10 degrees warmer, the lifetime is only half, and then it will only 5 years.